So I'm really glad that you're all focused. There was a request to go over the last problem from the last assignment. Okay, so um, I'll do that. Keep doing what you're doing. Okay, you don't have to pay attention. All right, but if you're interested, maybe this will be somewhat helpful. Okay, so we have a beam, right, that has a distributed load on it. Okay, but it's only on that one portion. Okay, so how would you go about figuring out what the internal bending moment is in that section? Well, it's the internal bending moment. So what's the approach? Like, what do you see? I guess I can show you how to do it the other way, and then I'll show you how to slice. Okay? Or I mean, you get on the slice, right? So here, oops, I have to. Okay. We want to calculating out the external equilibrium first, right? Okay, at all the boundaries, right? So figuring out what P and Q are, okay, with this load. This load is 10 kilonewtons per meter. Make it a little bit bigger. Okay. Right, we want to figure out what the equivalent, right, external load is, right? It's 1 kilonewton, and it's acting halfway in between the end of the beam. So when we look at doing equilibrium on the entire system, all right, what we have is P plus Q minus that 1 kilonewton for the equilibrium of the forces, right? And what we have for the moments, right, is that this Q, if we say at P, we do the moments here, right? If we do that, I'm gonna minimize that for a second. If we do those moments there, okay, then we can say, all right, there's a contribution from Q, half meter away. There's a contribution here at 0.55 away as well. Okay. And we don't have to worry about P because we're doing the moments about P. This is just for the external equilibrium. So then we can figure out what P and Q are, right? So we know what they are there. What do we do next? Well, if we are using the integral form, okay, what we want to look at is what is happening at the left and the right, okay? And for that, we're going to just go a little bit to the right of P and a little bit to the left of Q. Okay? Or I'm sorry, we're going to go a little bit to the right. Sorry. We're going to go to a little bit of the right, okay, of P, and then from the right, we're going to go a little bit left of the entire overhang. So then we can figure out what the internal shear and bending moment are at the right side and what it is at the left side as well. And if we look, we really actually didn't even need P and Q here, right, to figure out what the boundary condition is at the right. So there is an approach that we could have taken where we just said, I'm going to take a slice and do internal equilibrium at the right side. Okay, that would have been another option. But what I did here, and what's in the solutions for this exam, okay, because we wanted to do a drawing of the bending moment and the shear force, right, is that we solve everything out. In this region over here, there is no distributed force being applied. Okay, so the integral of 0, which is what you would use to calculate the internal shear force, that's going to be equal to 0 plus a constant. Okay? So for that region, we see that it's just flat. Okay? And then what do we have? We have a jump in the beam here because we essentially have an F-app, okay, being applied by that support. Okay, so that F-app leads to a delta V, a positive delta V, right? And what is the quantity? It's the Q. It's the 1.1 kilonewtons, right? So that's this. We go from minus 0.1 kilonewton, then up to 1 kilonewton right here. Does that make sense? Okay, I'll try to make it a little bit bigger. I know it's hard to see because we are down a monitor. Okay, and then we ask ourselves what's happening from here to here. Well, there is a distributed force there, right? There is this distributed force being applied there. So we have to integrate that one. Okay, and when we integrate it, well, first that distributed force has a negative W naught, essentially. That the W naught being the 10 kilonewtons per meter, or the minus 10 kilonewtons per meter. So then we're going to have a downward slope, okay, and it has to come out to meeting the boundary condition that we already solved for at the right. What do we do for the moment? Well, we can integrate up as well. Okay, so we can say, all right, we've calculated out what the internal shear forces look like. Now we have to figure out how to figure out what's going on with the moment, and we can integrate these to find this curve. What's that? You didn't get the last one. Okay. Well, dn dx is equal to, what is dn dx equal to? Right. Okay, so if I put the dx on the right side, and then I integrate. So integral of dm, right, is equal to m, and so that's equal to the integral of v dx. Okay? All right. So we can write out expressions for the internal bending moment in this region and this region. Now this is the region that we're interested in, right? And maybe the confusing part of this question is we said it's from the right, okay? But the expressions that we've derived here, they are actually, if you look at them, they're coming off from the left side. So x is from here to here, and x prime is this direction from here to here. So we actually have to do the right quantity, like a d minus that x prime, okay, to figure out what the bending moment is at that location. Because our coordinate system, right? Our coordinate system here is x prime. Okay? But we said that we want a distance coming from the right, d. Okay, so to figure out where we are, right, where we really are, we're going to plug in not x primes, but we're going to plug in d minus x primes. Okay? There is arguably a simpler way, though. Okay? To find that bending moment, right? What we could have done at the very beginning, all right? If we're just interested in that location, right? We have here this distributed force being applied, right? And it keeps going, but we're only going to our location D, right? This is D. This has quantity minus W naught, or we could say W naught, okay, whatever it is. So if we do our equilibrium at this location, O, we're going to draw a V, we're going to draw an M, like we see there. Okay, we're going to draw these. We agree with these conventions and the V's and the M's. Okay, so what is, if we do equilibrium in the y direction, what is V equal to? Well, maybe I should do it this way. V minus what is equal to 0? Right? Huh? Oh yeah, sorry, it's D, yes. See ya. Okay, so that is the expression that we have for the shear force, right? And what are we going to have for our expression for the moments? Okay, we're going to be looking at, if we do it at O, we have some Vx, which is negative, right? Okay, and we have a minus M, okay, that's also negative, right? And then we have a positive contribution, right? Okay, let me put it this way. It's W naught D is the quantity, right? And then it's acting at a distance D over 2. Because this, the effective, right? This effective W naught D is acting halfway down the beam. Right? This is a distributive force. Okay, and so when I look at where is it acting when it's creating the moment, it's acting halfway down. It's, well, yes, that's where we say the centroid of the distributed force is. It's acting halfway, yes. Okay, so that's why this comes out to be this term right here, and this is going to be equal to 0. Okay, so we had that V is equal to W naught D. Okay, W naught, the way we've defined it, is the 10 kilonewtons per meter. So that's important to keep in mind. Whoops. Okay. So now we can write in that we have minus W naught D, and I guess I should have written, this is D as well, right? So this is D squared minus M plus W naught d squared over 2 is equal to 0. Okay, and so m is going to be equal to w naught times quantity d squared over 2 minus d squared. Okay, and so this is just so this is another way to do it. If you're just interested in the location. But once you find that location, then we need to calculate the bending stress at that location. You can do it this way as well. If we don't ask for the shear force diagram, we should be able to do it both ways. Okay. Oh, we were just doing that. Oh, no, we weren't. Well, that's right. Okay, that's what that is. Okay. No, just yeah, okay. Okay.
If we're fine. Do you know the formula for the transverse? No. Do you know what the formula is for shear stress? Once you find the
This is also the everything in general for everything here as well.
so and take out L.
This is I'm not quite sure.
One side.
Double check, make sure that
breakdown, moment inertia, everything.
Oh, it's just half of that, right?
Break down everything.
Yeah.
Yep. Get L,
Yeah, well, I'm
H,
giving it
isolated.
from,
Right.
well, I'm giving it,
Try that first. Are you getting
I gotta do force equilibrium, right? So this plus this minus that, right? And I've also got to do the moments, right? But this is what you should get. And I agree. You get the shear, at least the way these are defined, the internal shear is equal to minus bar r. Okay? Okay? And at the left side, I get internal shear is equal to RL. Yeah. Okay, right? Because you just go a little bit over, right? So look what happens. It's kind of fun. Right, we said that we had RL on the left side, right, which is 3F over 4 plus MF over L. If I subtract FM from there, okay, so I get RL minus FM, I get a minus FF over 4 minus MF over L. Okay, because we see, because I just, oh no, plus MF over L, right, because I'm just subtracting FM, right? Because that delta V, right, if I look at my equations for advanced elections, we have a concentrated force. Delta V is equal to FF, right? And in this case, FF, though, is not in the positive direction, it's in the negative direction. It's not in the plus Y direction, it's in the minus Y direction. Right? So that's what you were talking about earlier. You were even saying it should drop, right? It should drop. Okay? But look what happens. It drops by FF. This then becomes minus FF. Okay? And this stays there. So minus FF over X.
What's your answer?
You were saying the shear
Oh,
force on the right portion is minus R. Minus R is minus FF over 4 minus FF.
We found that, baby.
Or plus MF. Without any numbers, you're just looking at the variables. It should work. I can keep it up for a second. Do the equilibrium, right? And and figure out what's up. And it's online. You just go to any of the websites, and it's the OneNote. That's under Office. Okay, and here you go. Okay, thanks for asking the question.
Oh.
Okay. Yes, Michael. Okay. Why do you think? Yes. But this is double shear. If you go back, if you open up the slides, right? If you go back.
Oh, because it's
P over 2A, because there are two, right? This one is the average shear stress for double shear is P over 2A because there are two interfaces. Well, so like the okay, so that's a good question, Mike, because I know that. No, I mean, well, no, you wouldn't know that. Well, you know it kind of like we're trying to figure out what the internal shear force is, right? And once we know what the internal shear force is, okay. It should be P over 2A. Yes. Yeah, it should be P over 2A. No, it's P over 4A.
That's because it's P over 2.
Right. But it should be P over 2A.
Oh, because P is the shear.
Area. If I take a cross-sectional area of B, if I take a cross-sectional area of B,
Nope, just getting the ratio.
But it's still, okay, so it's still over 2A. Just I just want to work it out.
Okay. All right. So, all right. Let me go to that. Where is? Okay. Okay, so everyone, your attention, please. Just for a minute, okay? And if you can see the screen better. This is the slide. If I could have your attention just for a minute, I'm sorry. Okay, so I made a mistake. Imagine that. All right. This is the slide shear and short beams. Okay, where we're comparing the shear stress in the single shear and the double shear. Okay, and I made a mistake here on the double shear. It might be helpful if I go back here. Okay, what we said for double shear is that the average shear stress, okay, is going to be F divided by twice the cross-sectional area. What's happening is you have these two sliding plates, okay, and you have one opposing plate creating shear, or two regions, okay, of shear here and here. And if I just look at what's happening on the right side, I can see that, oh, I've got some shear stress being induced, like look down at this one, okay? I've got some force, F over 2, acting over this area, and that's got a shear stress here and another shear stress on this opposite side. And the force is F over 2, and the area is A, okay? So this should be F over 2A. Now, when I came over to here and I use a 3-point bending system, okay, we see once again that P over 2 and P over 2 are the reaction forces, or F over 2, like what you have over here. These are the reaction forces, and in reality what we're looking at is this cross-section and this cross-section, okay? These cross-sections are going to have area associated with them, and they're going to also be area A. Okay. So when I did this out, I was thinking, oh, it's F over 2A because that's what you get with average shear stress for double shear. But in reality, it comes out to work just like the previous example should. It should be P over 2A, okay? So I'll have to make a note in the video that's up, but that should be P over 2A. I apologize for that. Okay, that's all. And that's going to affect question 2. All right. So I had to fix question 2. So if you did number 2 already, I apologize. And if you're looking, you will now see the answer to number 2, which is different than what I just had. Okay. All right. Okay. I apologize. I made a mistake. Okay. Yeah. So here you go. Everyone, you get a freebie here. Okay. This is session 14, question 2. All right. And what I did wrong, right, is I had f over 2a, and then I used what I had written there and wrote f over 4bh. But really, it should just be p, okay, p over 2bh. All right, because it's p over 2. So when you do this out, this should be 1/2. No, this should be, yeah, 1/4. And this ends up being h over 6. Okay? Other questions?
Literally Jackie.
You take a look at what others do.
You're not gonna
you're absolutely right. So what's going to happen is keep going down the slope, and it's going to be a sharp problem. Right, but the slope is getting so the area under this thing, yes. So the area under this one is this one. Yes, but it goes, it drops below. It has to drop below because it has to meet the end conditions that there's zero delay. Like that. Good. No, but it goes below. It has to go below the zero.
Our club is shit.
Yeah, the club
What
drops.
do you mean by height? No, they're high rank. You don't even
So
play.
full turning length has no height. The slope is the
You don't
same,
play
but it should
club.
be.
You did not.
Okay.
Why was the top contributor?
Take a look at the one.
I think you did it.
Yeah. But, yeah.
Why? Yeah, I'm literally the top. Why?
Yeah, I think. So here's the okay. So
That doesn't mean you have to delete it.
they're combining two ways. One, if you're going to do differential intervals, then you don't have to do internal cuts. You don't do method of sections. I mean, we had to do kind of method of sections.
You said you
here,
deleted
what's
it. You
happening
were
on
on one day.
side.
Yes, I
But after
deleted
that,
one day ago.
this interval based on the distributive force. So you're saying you can't. No, you can use the interval method. Right? Just what's happening there is there's a couple of moments. Right? And for a couple of moments, a couple of forces, right, where we have distinct pools that we need to apply. But yes, if you decide to go interval method, you don't need to do any more method of sections.
Never used it for statics.
Never. Writing takes
The height is h.
yeah. That's it. So it's times the height of
Okay, sure.
in this case.
You want me to upload? So
Yeah. Because in this case, we consider a bar. We have to find. We have to consider not only where it distributes, but height. So we divide by two. So
I can fix it.
Yeah, and then right
you
face
face
Thank you. I knew that in the end, I think it comes out right, but yes, thank you. Okay, so. Oh, okay, so wait a second. This is 8. This is 3 halves. P over 2BH. Okay, so is this what you got?
Yeah.
That's what you got?
Yeah.
Okay. Sorry, everybody. Again, bubito. Boo boo. Sorry, everyone. I don't think so. I think I did 3 correctly.
I understand that.
I don't have my keyboard. Goodness.
Oh wait.
Okay.
Wait, which makes sense because you're only going from that central part.
Okay. All right. That should be correct now. Okay, so there it is.
So that means that the area
Yes.
is only half of one face. That means B2 divided by 12. B2 divided by 6 would be one face. B2 divided by 12 is half of the face. Actually, that makes sense. Okay, so look at the question you're asking. It's asking, at what length will L, at what length L will the average shear stress of half maximum length what is that learning? I think when you, if you look at the graph,
Okay.
so the shear, this is the shear. The moment, the maximum moment, that's half of the shear force. The shear force is half.
Okay. So if you go back to slides, explain that.
So,
Double shear.
I tried doing this, but I just got 0.
Okay. Well, the moment is 0 at the end.
Yeah.
Okay, but it comes up to PL over 4 in the middle.
Oh, so you have to graph it to find the max? Yes.
Yeah, so you can look at it a couple ways, right? So one, if we see here that we have, we agree, right, with this shear force diagram. Okay, this is going to be P over 2, and then we have this P downward, right, which is like the minus FF, and it drops like that. So, and we also agree that there's going to be 0 moment applied at these ends,
Yeah.
right? So we know we're going to start at 0. Okay, and we know that the slope is P over 2. Well, P over 2, and then we go up to, or we go over to L over 2. P over 2 times L over 2 is PL over 4.
Okay.
That's how we peak out there.
Okay.
Yeah. Good. I'm glad you asked the question.
Wait, sorry, follow up.
Uh-huh.
So if we did, because I did the external equilibrium like at this point here, right? To find for the moment.
Sure, that's you.
But then I got 0. But if I did it here, would I get P over 4?
Yeah, you get P over 4 in the middle.
Okay.
Absolutely. The internal moment at the left and the right side has to be equal to 0
Yeah.
because there's no moment being applied by these
Yeah.
supports.
Okay. Thank you.
And there's not there's not there's not like a moment being applied
Yeah.
or like right next to it. Good. Okay. So there will be, just for everyone's information, there's one more problem that I haven't put on Canvas yet, but I will put on Canvas. Yeah. But
The others at it's basically when you find the external limits.
yeah.
Because the thing is take everything start at 1.
Oh, okay. We had to go to a surface. So going to a surface means you go up and you go axis, right? Go down. No, don't do that. that is the full. We agree on that, right? What I think, and one of the reasons why we do these exercises is because we often get
Yes.
yeah, but we get confused. That
That's what I'm trying to
bending stress is at like half of shear. Okay. And so that's got to be half. It's got to be half the height. You guys
That'd
looking,
be
you looking
like
incredulous at me.
that would be like considered the variable y,
Right.
But in this equation for this equation, right?
Well, now you're doing transverse shear stress. That's different.
Yeah, so there's no y there. But when
Right.
we use this equation for question 3, it says that thickness is equal to height instead of equal to this. But when we plugged in
Yeah, thickness. No, thickness. T. Now we're talking about different things. T for transverse shear. Okay. Yes. T is equal to the base. Angular cross sections. Yes. I thought we were talking about bending. Yeah, that is. Oh, you're not about transverse shear. Yes, and yes. Yes.
So I can hold the question. I think it says thickness to the height.
Yeah. I was trying to be helpful. That's a bending moment question, isn't it? Oh, it's a bending moment with. I know what you're talking about, right? You're talking about.
Yeah, it says thickness slash height 4 centimeters.
Okay.
We had lucky numbers.
Okay. So yeah. So well, it says H, right? Well, okay. In this, right? If we look at this, I meant okay, but you got a number, so it doesn't say what it is. All right. Yeah. Yeah. Okay. So I was trying to be helpful, but I ended up being less helpful. Okay. Yes, you need to make sure you convert over. Yes. Hmm?
Oh, megapascals.
Yeah. Base B, height H. Yeah. It doesn't. I don't mind. I can change the wording here. We're just. Nothing changes with the numbers. We're just removing that word thickness. Okay.
Let us see.
Yeah. It does. We are looking at the shear. Okay. And as
Yeah.
Finish all the problems. Can't be doing this no more, boy. Bet you get 3. Yes. It's good, Shear. My new family is going to be.
Thanks, guys. I apologize for some of the confusion. Thank you, everybody. I apologize for some of the confusion. Next exam, it's on the syllabus. It's I don't know. I don't remember the date.
Day 2 after spring break.
I think it's even more than that.
More than that.
I think so. Yeah.
Because I was just looking at the exam and they had a lot of. I didn't know like anything on the exam, so I was like.
It'll work out. It'll work out.
Hopefully.
I hope. I hope it'll work out. Okay.